1, right? Would you agree? Like, yeah, like we did 15, but we started with 15.1, and then we did 16, and that was 16.1, and now we're doing 13, and now we're starting with 13.
We started with 16.2.
Oh yeah, we started with 16.2. Actually, that's right, because I wanted to leave the easy stuff for when I was gone for that Friday. So that's true. But we're doing we're gonna do. Yeah, there we go, 13.3. Now, starting off with 13.3a, because this, technically, I like to follow your textbook as much as possible. Maddie, there's some stuff in the green bin, if you want to grab it. There's 3 things in the green bin. That's because this definition of oxidation and reduction is actually in 13.1 of your textbook. We're starting in kind of a weird spot, but that's because I think it's the most useful tool to put in your tool belt for this entire unit. So in the last unit, we had a lot of tools that we put in our tool belt, right? We had major entities, we had using the table of acids and bases, we had being able to rearrange equations, we had the square root problem, we had the approximation problem, we had lots of tools to put in our tool belt that we could pull out and use every once in a while. And we're going to talk about oxidation numbers today. Oxidation numbers are probably the most important tool to put in your tool belt for a redox unit. Hopefully that kind of makes sense. So I got my hot water going. That's fantastic. I'm just going to let that chill, and we'll come back to that. Oxidation and reduction. Is anybody familiar with those terms at all? Sienna, there's 3 things in the green bin if you want to grab them. Has anybody ever heard of oxidation or reduction before? Sky?
I've heard of oxidation. That's rusting, right?
Yeah, oxidation you probably have seen before or heard before. Okay, oxidation is typically, that's the process of rusting, right? So has anybody ever seen rust before? Yeah, you have. Of course you have. What does rust look like? Oh man, you guys are really quiet. Holy guacamole. Yeah, Jaden. It's like a reddish browny material, and it flakes off of really crappy old cars, or really nice old cars maybe, but not so nice anymore, that kind of thing, right? Some properties of rust are that it's brittle. And where does the rust come from? What does rust like to form on? Iron, yeah, specifically iron. That's usually what we're talking about, okay? Now, but it doesn't have to be iron, okay? This is silver. It's not very nice, but it's silver, okay? It's got some shiny parts to it. The blade of this knife, I don't know, like a huge ass butter knife or something, okay? The blade of it is super shiny, nice and neat and beautiful, okay? But the handle, ugh. What the hell is going on there? Have you ever seen this kind of stuff before? This is what happens when silver oxidizes, kind of, okay? But do you know what this is called when silver rusts? We don't say that it rusts.
Varnish.
It what?
Varnish.
Oh, not varnish. You're so close. You're so close. Not varnish. What? It tarnishes. Have you ever heard that before? Tarnished silver? You've never heard that before? That's okay. Whatever. That's fine. So, tarnished silver is not because of oxygen. Like rust is because iron interacts with oxygen and gets oxidized, okay? But tarnished silver is not because of oxygen. It's in the same family as oxygen, though. Let's take a look at where oxygen is, the periodic table. It's in group 16. It's kind of the first element in group 16. And what's immediately below it? Ooh, sulfur. Sulfur compounds often smell gross, okay? And we might make a gross smelling compound today, but that's whatever, that's fine, that's okay. This is tarnished sulfur. It's silver, tarnished silver. Ooh, man. This is silver sulfide. Tarnished or rusted iron is iron oxide. Okay? Now it's basically the exact same thing, except silver's really, it really resists corrosion against oxygen, but it can't resist corrosion against sulfur. And you'll talk about that if you take the university level chemistry. So silver sulfide we can untarnish. I don't know what the right word is. We can we clean, yeah, kind of polish, except polishing is like literally removing the layers of crap from your thing, right? That's what polishing is. You're like buffing, or you're taking small layers off of something. We don't want to buff or polish this necessarily. We want to chemically return the silver sulfide into what? Solid silver. That's what we want to do. And so we're going to use a redox reaction in order to do that. Now I need some things in order to do this redox reaction. I have a little bit of salt. Okay, we'll talk about that later. Ooh, I got baking soda. That's what I'm talking about. I got aluminum. Fantastic. So I'm going to take some aluminum, and I'm going to do my best. Yeah, that was pretty good for me. Okay, so I'm going to take my aluminum, and I'm going to put it at the bottom of the baking pan. And I'm going to take my tarnished little tiny teaspoon, which I've never used before, and tarnished whatever you just butter knife. And I'm going to take some baking soda, and I'm going to spritz some baking soda in here. And I'm going to pour some hot water all up in this grill. Yeah. That's what I'm talking about. Hopefully there's enough. Hopefully there's not enough. But whatever. And add some more baking soda. And we'll come back to it later. Ooh, that's really hot. Woo! It's very scientific. It's very quantitative what I'm doing. It's not at all. That's fine. Okay, perfect. So we're going to leave that in there for a little bit, and then we're going to come back in like 5 minutes. Is that okay with you? And just for good measure, I'm going to add some salt. And we'll see how it goes. Okay, so we'll come back to that, and whatever, that's okay. Don't worry about it. Historically, the term oxidation has referred to when metals react with oxygen. Does that make sense? Are we okay with that? Oxidation is reacts with oxygen to make something oxide. The opposite process, reduction, was when metals were produced from compounds. So let's take a look at this, and let's identify these as oxidation or reduction. And we'll talk about why reduction was called reduction and why it makes sense from a historical perspective. So here, let's think about this for a second. Is this thing reacting with oxygen? No. So it's not a historically oxidation term. Okay, that's totally fine. Are we making a metal from a compound? Yeah. Yeah, we're making a metal from a compound. So what's that? It's reduction. Good. That's reduction. Nice. Here we have magnesium reacting with oxygen to make magnesium oxide. So what's that? That's oxidation. Perfect. Now we've got nickel oxide reacting with hydrogen gas to make nickel and water. Is that oxidation or reduction? Reduction. That's reduction. Now, what I want to say is the reason why this is called oxidation and reduction. Oxidation makes sense, reacting with oxygen. Okay, whatever. Here, what do you think weighs more? If I had 1 mole of iron 2 oxide, or if I had 1 mole of iron, which one would weigh more?
Iron 2 oxide.
The iron 2 oxide. Would you agree this has a larger molar mass than that? Okay, so the idea behind reduction is if I took 1 kilogram of iron 3 oxide, I would make less than 1 kilogram of iron. So when you take the iron ore, when you take this compound and you reduce it, the reason why we call it reducing is because you get less mass out of it than what you put in. Does that kind of make sense? That's why we call it reduction. If you start with 1 kilogram, you're going to get less than 1 kilogram. That's why they historically called it reduction. So oxidation and reduction, hopefully that kind of makes sense. Okay, but that's crap. Nobody wants historical definitions. Because remember, we had to redefine acids and bases a couple times, right? Our first definition of an acid, way back in grade 9, our first definition was anything that had hydrogen ions in it. And then we had to redefine it, anything that made hydronium and water. And then we had to redefine it, anything that donated protons. And in university, you'll redefine it again for Lewis acids, okay? So our historical definitions often don't hold up properly for a lot of things. Here's our modern definition of oxidation and reduction. Oxidation is the process of losing electrons. Reduction is the process of gaining electrons. Does that kind of seem familiar?
Yeah.
Yes.
That's very similar to our Bronsted-Lowry definition of acids and bases, isn't it?
Isn't that like exactly, or isn't that similar to what the Lewis acid definition is too? 'Cause
Well, it's very close. It's extremely close to the Lewis acid definition of acids and bases.
oh no.
If you were up here, you would smell something kind of gross cooking, but that's fine. Whatever, it's okay. We will need some new ideas in order to identify whether substances are losing or gaining electrons. The first and possibly most powerful tool in our tool belt is oxidation numbers. Okay, now there's something you have to remember. It's a mnemonic device. It's a way of being able to remember different things, right? Has anybody ever heard the mnemonic device, never eat soggy wieners?
Yes.
What does never eat soggy wieners mean? I see some people going, oh. Okay, David, what is it?
It's for like northeast, west, and south.
Yeah, that's right. If you started, from my perspective, right? From my perspective, if I went, never eat soggy wieners, that means north, east, south, west, right? So that's what it means. It's a mnemonic device to be able to do that. Has anybody ever heard of King Henry died by drinking chocolate milk?
Yes. Yeah.
King Henry died by drinking chocolate milk? Yeah. That's a mnemonic device to remember the metric prefixes. So kilo, hecto, deca, and then your base unit, and then centi, or deci, centi, milli, blah, 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 that kind of thing. So here, we're going to try our best to use another mnemonic device. Whatever. Kind of, sort of, maybe? Yeah? If anybody who's familiar with astrology, by astrology, whatever, okay? But Leo is a what? Leo is a lion. No, I keep forgetting to bring money. I'm so sorry. I keep forgetting to bring money, but I promise you, I will have money next week. Sorry. That's 4 or 5 weeks in a row. I feel terrible. I put it in my pocket, and then I just have money in my pocket all day, and then I go home, and then I throw my pants in the laundry, and then I get coins in the laundry.
Are you legitimately like forgetting, or are you just like making that up?
No. I'm honestly I bring it on Monday, and then I put the coins in my pocket, and then I just don't I don't ever have my hands in my pocket really.
Oh,
so
I thought you were just making excuses.
No. I mean, you can think that I'm making excuses, but I'm not. Okay, Leo is a what? Is a lion, right? And Leo the lion goes grrr. Yeah, that's right. When you lose electrons, that is the process of oxidation. When you undergo oxidation, you are oxidized. When you gain electrons, you undergo reduction. Now, what I want to kind of like focus your attention on, okay, that's great. Losing electrons is oxidation, gaining electrons is reduction. That's fantastic, whatever. But if you don't know when something gains or loses electrons, that's really tough. That's really, really, really tough. For example, if I have silver that turns into silver ions, I'm curious, did that silver, the silver that we started with, this silver that we started with right here, did it gain or lose electrons by turning into silver ions? What do you think? Electrons are what? Negative, right? So if we gained a negative, we would become more negative, right? So did it become more negative? No, it became more positive. Now you can't gain or lose protons. Like a compound can, but an actual element can't gain or lose protons, at least not outside of a nuclear reaction. Okay, so this silver, if it gained an electron, it would become negative, right? We didn't become negative, we became positive, so we obviously lost an electron. So this is the loss of one electron. And when you lose electrons, what is that called? Oxidation. That's called oxidation. And the reason we're hopefully going to remember that is loss of electrons is oxidation. That's perfect. Hopefully that hopefully that makes sense. Can I move on? Yes, perfect. Now we're going to talk about oxidation state and oxidation numbers. Perfect. Okay. So when I take a look at my silver spoon, it's not perfect. It's not amazing, but it's a whole heck of a lot better than it was originally. Is this pretty shiny? Yeah, that's not bad at all, right? Okay, that's pretty good. And then when I take a look at my silver knife, the handle was pretty gross. It was pretty grungy, okay? And I'm going to take some of this grime off of here, okay? And so the handle, I don't know, I feel like it looks a whole heck of a lot better than it did originally. Would you agree?
Yeah.
Yeah. And so, okay, we'll come back to this. I'm gonna take this and I'm gonna put it in there, and I'm just, oh man, that's what I'm talking about. Yeah. Okay. So our silver sulfide has reacted with the aluminum. It has to be in contact with the aluminum foil to turn into silver and aluminum sulfide. The kind of gross smell I totally missed. That's okay. The kind of gross smell that I smelled up at the front was hydrogen sulfide gas. It was making a little bit of hydrogen sulfide gas. And if anybody knows anything about hydrogen sulfide gas, it's incredibly poisonous, but also smells like rotten eggs, so whatever. The oxidation state of an element is the apparent charge, okay? It's the charge you kind of give it that an atom would have if all the electrons in a covalent bond belong to the more electronegative atom. Okay, so the way we're going to think about this is we're going to draw FCl, the compound FCl. Now the compound FCl is basically F bonded to what? Cl. All right, perfect. Okay, FCl, nice. Now this bond represents how many electrons? 2. Represents 2 electrons. Now it represents 1 electron from the fluorine and 1 electron from the chlorine. Is that okay? Every covalent bond is a combination of 2 electrons. So this is a tug of war. Do you remember this from last year, from Chem 20? Yeah, this is a tug of war between these electrons, and who is winning the tug of war between the electrons?
No.
Do you remember? Let's take a look at fluorine. What do you know about fluorine and its ability to pull in electrons?
Very strong.
Sure.
Ooh, it's got an electronegativity of what? Well, not a bajillion, but about as high as it can be. It's got an electronegativity of 4. So this thing's electronegativity is 4.0. Do you remember that?
Yeah.
Kind of? A little bit, okay. And then what's the electronegativity of chlorine?
3.2.
3.2, which is still pretty good, right? That's a pretty wicked electronegativity, but whatever, okay. So who's winning the battle for the electrons?
Fluorine.
Fluorine is winning the battle for the electrons. Now, fluorine came into this sharing 1 electron. So the black electron always belonged to fluorine, okay? It always did belong to fluorine. So by it winning that electron, it didn't gain or lose any, okay? But what else did it gain by winning this battle? It gained the electron that chlorine used to own. Is that okay? The fluorine is winning the battle for chlorine. Now, it doesn't totally win. It doesn't turn into an ion. But we say that the fluorine is winning the battle. So if it has temporarily gained an electron, what temporary charge do you want to give it? If something gained 1 electron, what charge would it have?
Negative.
-1. Okay? So we would have an oxidation state or an oxidation number of -1. And chlorine, if it temporarily lost an electron, what kind of an oxidation state would it have? +1. Now that seems crazy because chlorine never forms positive anything. Now keep in mind, these are not ions. All we're saying is who's winning the battle for the electrons. There's no ions being created. Chlorine is not forming a +1 ion, but it's losing the battle to somebody else, so we say it's got a +1 oxidation state. Is that okay? That's all we're saying. Perfect. So now let's take a look at H2O. H2O. Nope. There we go. Perfect. H2O. Now each bond represents how many electrons again?
2.
2. So let's have 1 electron. The blue electron is from hydrogen, and the black electron is from oxygen. Sure, whatever, doesn't matter. Who's winning the battle for those electrons?
Oxygen. Okay. Yes.
What's oxygen's electronegativity?
3.4.
What? 3.4? That's huge. What's the only other element that has a higher electronegativity? Fluorine. That's the only other element that has a higher electronegativity. Oxygen has the second highest electronegativity out of anything else. Okay? So would you agree it's winning the battle? Okay, so not only does oxygen gain back its electrons, it gains back its electrons, so that's nothing. That's no gain and no loss. But how many electrons is oxygen winning right now? 2. 1 from that one and 1 from that one, so it'll be -2. What about the hydrogens? +1 and +1. Is that okay? What do you notice if we added up all the oxidation states in this compound? What do you notice it adds up into?
The charge.
It adds up into whatever the charge on this entity is. What's the charge normally on H2O? Charge is 0. So this should add up to be 0. Okay? Does that kind of make sense?
Yeah.
Yeah, kind of makes sense. Perfect. So oxidation numbers are useful in tracking electrons gained and lost during reactions. So we got to go through some rules to see some stuff about oxidation states. So I can't remember, there's like 6 rules or something like that we have to know. Most of them are pretty easy, but some of them are a little bit difficult. the oxidation number for ions is equal to the ion charge. For example, calcium 2 plus. Like, how many electrons did it have to lose in order to turn into 2 plus?
2.
Okay, so does it make sense that we will assign it an oxidation state of +2? Now, usually, a charge, we write number first and then sign. Would you agree? Look at all the charges on your periodic table or on here. They're number first and then sign, and that's kind of weird, right? But that's the way we write charges. 2 plus or 3 minus or something like that. But how am I writing my oxidation state? +2. I'm not going to dock you marks on it, but I just want you to understand that that's typically the way we write oxidation states. Okay, what's the oxidation state of this sodium right here, right now? +1. It's got a +1 oxidation state. Why? Why does it have a +1 oxidation state?
It was 1.
Because its charge is +1, right? Yeah, good. Okay, well, KCl. You guys know anything about ionic compounds?
Yeah.
Some of you do, right? So what is an ionic compound? How can you spot an ionic compound from a mile away?
Start with
Starts with a metal or
ammonia.
ammonium. Starts with a positive ion, okay? This is a positive ion. This K is a positive ion. Can you convince yourself that that is a positive ion?
Mm-hmm.
Yes. If you cannot convince yourself that that's a positive ion, you need to show up at or you need to stick around at lunch, or you need to talk to me, because you're about to enter a world of hurt if you cannot recognize an ionic compound. Okay, so this K is really K plus, and the Cl is really Cl minus. So that K is +1, and that Cl is -1. Does that make sense? They're ions in an ionic compound. Okay, no problem. Now let's take a look at this. Is this an ionic compound? Yeah. What's the first ion you see? Sodium. And what charge would it have if it was an ion? Plus. So +1. Good. Now we'll deal with the rest of this thing later. Okay? But what is the charge on the whole thing? This whole kit and caboodle, HCO3. What's the charge on it? -1. Okay, so just keep that in mind later. Oxidation numbers for elements or molecules are 0. So the whole thing adds up to be 0. Okay? I'm going to draw something for you. I'm going to draw you what P4 looks like. Can I do that? It's this is not really, but this is kind of a bastardization of it, whatever, that's okay. P, 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 P. Ooh. Okay. So let's take a look at it. This P, it's bonded to that P and that P. So this P, how many electrons is it winning from that P and that P?
None. Wait, but it's the same, so it's not.
Well, what's the electronegativity of P? 2.2. And that one's 2.2, and that one's 2.2, and that one's 2.2. So how many electrons is this P winning from that P? None. It's winning back its electrons and no more. Does that make sense? So what's the oxidation state of this P? 0. It hasn't gained or lost any. What about that one? 0. Hasn't gained or lost any. Okay? So does it make sense? If you just see an element is something either by itself, in which case it hasn't gained or lost any, or it's something bonded to itself, in which case it hasn't gained or lost any. So what's the oxidation state of all 4 of these phosphoruses? 0. What's the oxidation state of all 2 of these chlorines? 0, and this zinc is 0. Is that okay? Hasn't gained or lost any electrons compared to its atom form. Okay, perfect. We're very quickly going to realize that hydrogen often has a +1 charge, unless it's hydrogen all by itself, right? Because what would be the oxidation state of H2? 0. because it's something bonded to itself. 0, right? Okay, but when hydrogen is in a compound, we give it an oxidation state of +1. Because often it's bonded to something more electronegative than itself, okay? The exception to the rule is metal hydrides. When's the last time you saw a hydride? Do you know what a hydride is? Well, what's the charge? This is lithium in a compound. Lithium, when it's in a compound, what charge would it have? +1, right? Would you agree? This is an ionic compound, right? It's a metal non-metal, so it's an ionic compound. Lithium has a +1 oxidation state. What does that mean hydrogen has to have? -1. And let's try and figure out why that is, okay? What's the electronegativity of lithium?
1.0.
It's 1.0. What's the electronegativity of hydrogen? 2.2. Who's winning the battle for those electrons, or that electron? Hydrogen is. That's why it's got a -1. Okay? So if it's a metal hydride, it's -1. But in every other case, I'm going to let you know right now, we didn't see a single hydride last year, or last semester, all semester. Okay? So that's just, tuck that in your back pocket if you need to, but whatever. That's not something you should focus on. This hydrogen, it's bonded to something more electronegative, so +1. And we'll just assume most of them are +1. So if this hydrogen is +1, what's that chlorine? -1. Boom. Nice. Zooming along here. Oxygen, remember, oxygen often, it's like really often is -2, right? With the exception of when it's bonded to something more electronegative. What's the only thing more electronegative than oxygen? Fluorine. So you got to be careful. You got to watch out for fluorines. Those are tough, okay? Oxygen is always -2 with the exception of peroxides and attached to fluorine. So for example, H2O. What was the oxidation state of hydrogen most of the time? +1, right? So this is +1. And this is -2. And what do they add up to be? They add up to be 0. Because there's 2 +1s and there's 1 -2. Would you agree? Is that okay? Okay, all right, perfect. Let's look at a peroxide. A peroxide is HOOH. So this oxygen, how many electrons is it winning? 1. Why is it not winning from the other oxygen?
Because they're the same.
They're the same, okay? So this is +1, -1, -1, and +1. So +1 and -1. We're going to do lots of practice, don't worry. We're going to do lots of practice. Just trying to let you know. Oxygen is bonded to fluorine. Who's going to win the battle for that electron? Fluorine. So fluorine's -1. That means oxygen has to be +1. Man. Okay. Okay, that's fine. The fifth and maybe the most important rule is that the sum of all the oxidation numbers of all of the entities inside that entity must be equal to the charge on the entity. What's the charge on this CO2 molecule? 0. So what's the oxygen? What can we assume the oxygen to be? Oxygen is mostly -2. So I'll say that's -2. Now, let's think about this. There's going to be a little bit of math, and just try and follow along. We know that there's 2 -2s in this molecule. So there's 2 -2s in this molecule. Do we know what the oxidation state of the carbon is? Have we learned a rule for the carbon yet? No, we haven't. So what I'm going to say is that we don't know what carbon is. I'm just going to write carbon. I'm trying to say I don't know what the oxidation state for carbon is, but I know that we've got 2 -2s. And when I add all the oxidation states up, what should they add up to be for this particular molecule? What's the charge on this molecule? 0. It's 0. So we have to do a little bit of arithmetic, a little bit of algebra. What does the carbon have to be in order to cancel out this -4? It has to be +4. Does that make sense? That's the only possible oxidation state that it can have. And when I draw the structure of carbon dioxide, hopefully this makes sense. This oxygen is stealing 2 electrons from the carbon, right? So it's stealing 2 electrons. This oxygen is stealing 2 electrons. So this carbon had 2 stolen that way, 2 stolen that way. So what's its oxidation state? +4. Okay? Is that all right? So the structure will kind of help you, but you don't even have to look at the structure. You can just look at the formula and figure it out. Now, this is where things start to get really, really, really tricky. And this is where if you follow this style of trying to solve for something, you will always be able to solve for the oxidation state. Okay? Is there anything in NO3 that we've got a rule about? Do we have a rule about nitrogen? No. Do we have a rule about oxygen? Yes. Oxygen is almost always -2. Okay? So what I'm going to say, I'm going to put, I'll do this in a different color, I'll put a -2 on top to try and show people that the oxygen is -2. Now, how many oxygens are in here? 3 of them. So we've got 3 -2s. And how many nitrogens do we have here? 1 nitrogen. And what should all of these oxidation states add up to be? -1. This has a charge of -1, so it should add up to be -1. So all you have to do is rearrange this equation. Now, for people who are crap at rearranging equations, this method is going to be very painful. The other way of thinking about this is, okay, if the oxygen is negative, what does the nitrogen have to be? Positive. Would you agree? It has to be positive, okay? If the oxygen is negative, how many negatives are here? What's the total negative charge? 6. -6. Do we want to cancel out all the negative charge? No, we want to have one left over. So we want to cancel out 5 of those negatives. How can we cancel out 5 of these negatives? +5. Or you could rearrange this equation. You could just rearrange it, do that in your head, whatever. Okay? So I'll add 6 to both sides, and I get n equals +5. So you'll get n equals +5, so +5. I really don't want to take a lot of time on solving that little tiny equation because that's like grade 9, it's even maybe grade 8 stuff, right? Okay, NH4 plus. Do you know anything about either of these elements? Do we have a rule for nitrogen?
Yes.
No. We don't have a rule for nitrogen. Do we have a rule for hydrogen? Yes. Hydrogen almost always is +1. Okay? If we look at our rule, hydrogen almost always is +1, except when metal hydrides. So when I take a look at this, all right, so hydrogen is +1. How many hydrogens are here? 4 of them. So we've got 4 +1s, and it has to equal +1. What does the nitrogen have to be in order to cancel out most of this positive? Has to be -3. Good. Hopefully that makes sense. You're just trying to figure out what that mystery charge is. Okay? All right. Perfect. No problem. Okay, now for a little bit of a tougher one. H2PO4. Do you have a rule about hydrogen?
Yep.
Yes, +1. Do we have a rule about phosphorus?
No.
No. Do we have a rule about oxygen? Yes, -2. So let's figure this out. Hydrogen is each 2 +1s. How many phosphoruses are here? 1. So +P. How many oxygens are here? So 4 -2s, and that has to equal -1. let's simplify this a little bit. What do all of our constants on the left side add up to? Plus 2 and minus 8. Plus 2 and minus 8 is minus 6, right? So that's like saying p minus 6 equals negative 1. What does p have to be in order to have negative 1 left over? Plus 5. There you go, plus 5. Boom! Lovely. That was tough. That was really tough. In a molecule, the more electronegative atom is the one that's assigned the negative oxidation number. But we already talked about that, right? We talked about that with OF. So, okay, whatever. That's totally fine. So here's a little summary table of all of our rules for oxidation numbers. Atoms in elements are always 0, right? Okay, sure. Hydrogen, most of the time, 99.999% of the time, hydrogen is plus 1. With the exception of a metal hydride, it's minus 1. Okay, sure. Oxygen is always minus 2, with the exception of peroxides. Again, we'll talk about peroxides a little bit later, that's fine. And then ions is just the charge on the ion. Perfect, no problem. So I got 2 questions for you. I want you to try and figure out what's the oxidation state of carbon in methane, okay? And then I want you to find out what's the oxidation number of sulfur in sodium sulfate. Sorry, this is my bad. I'm using the British spelling for it. Does anybody know the formula for sodium sulfate? Jaden?
Na.
It's going to be Na, and it's going to be SO4. But this is an ionic compound. In an ionic compound, you have to look at the ions to determine the formula, right? Ionic compound, this is an ion. What's sodium's charge if it's an ion?
Plus 1.
Plus 1. What's sulfate's charge? It's 2 minus, right? So what's the oxidation state of sodium here? Plus 1. Boom. Okay? Do you know a rule for sulfur? No. Do you know a rule for oxygen? Yes. So just, it says sodium sulfate, but just look at sulfate, man. Just try and figure out what the sulfur is in sulfate. So I'm going to give you like 30 or 40 seconds. And I'm going to walk around and you throw something at me if you want. Yeah. Correct. Perfect. Hopefully, hydrogen's plus 1. The whole thing has to add up to be 0, so carbon has to be negative 4. Good? Yeah, all right. So, yeah, whatever. We'll talk about that later. So let's take a look at sulfate, SO4 2 minus. So we don't know what sulfur is. Okay, so I'll write S. We know what oxygen is. 4 minus 2's, right? There's 4 minus 2's here. And then the whole thing has to be equal to minus 2. So this is S minus 8 equals negative 2. So if I add 8, S has to be equal to positive 6. So positive 6. Good? Ah, nice. Easy peasy, lemon squeezy. Okay, so let's do some more practice. I want you to take a look at this, and I want you to ask yourself, is there anything in here that scares you? Is there anything in here when you look at that formula, you're like, whoa, man, I don't like that at all? Let's take a look at the first one. Do we have a rule about nitrogen? No. Do we have a rule about fluorine? Kind of. What's unique about fluorine? It's the most electronegative, right? The most electronegative thing. So let's take a look at this. It's going to be negative, right? And it's going to be negative 1. So what does nitrogen have to be? Plus 3, right? Because there's 3 negative 1s, so we need plus 3. So it's oxidation number, right? The oxidation number of the underlined thing is plus 3. Okay, no problem. Do you want to do any other ones together?
Yeah, that's it.
The S8? Sure. 0. Why? Why is it 0? It's an element all by itself, right? Another way of thinking about this, you could set up an equation for this if you wanted to. You could set up an equation, okay? How many sulfurs are here? 8. So 8 S's, it has to be equal to what? What's the charge on the whole thing? 0. So if I divide by 8, that means the sulfur is 0. You know what I mean? So there's lots of ways of going about solving these oxidation number questions. Is there anything else on here that scares the crap out of you? What? The PBI4? PBI4, sure. That's a tough one. I totally agree. Take a look at PBI4. Do that one right now. Take a look at PBI4 and try and figure out how you could do this. I'll give you 30 seconds. Did anybody get that the lead is +4 and the iodide is -1? Yep. Okay, there's a super easy way of dealing with this. What kind of compound is this? Ionic. It's an ionic compound. So look at the ion charges. Do you know lead? Lead is multivalent, right? Do you remember that? So that kind of sucks because we don't know what the charge is on lead. But you do know what the charge is on iodide, right? The iodide has to be -1. It's iodide. That's what an iodide ion is, -1. So when I look at that ion, the ion charge is -1. So what does the lead have to be? +4. that okay? I'm gonna give you, I don't know, I'm gonna give you like 7 or 8 minutes, go through this and try and figure it out, and then and you know, collude with your friends, right? And try and see if they have the same answer as you. And I'm gonna be going around putting out fires, maybe. Maybe I'll put out some fires, we'll see. That. Oh. There we go. That's okay. So, what I said was this is an ionic compound. So if it's an ionic compound, we need ions. And we can treat the ions independently of each other. So the iodide, I as an ion, iodide as an ion, will always have a maximum charge. That's the only possibility for it. But it's just that if that's it by itself as an ion, it's minus 2. But perfect. Yep. The I here, right? Yeah. Treat the ions separately. Okay? Treat the ions separately. So you have in there, you've got, what's the first thing you see? Potassium. And potassium always has a +1 charge when it's an ion. So you've got 2 of these, and then what's everything else? Everything else together. H, 3. Okay. So if you've got 2 Ks and they're both +1, what is this whole thing have to equal? The whole thing, this entire thing. Okay, let's think about a different one. Let's think about a different one. Yes. You have K2H3iO6, right? But we already know this potassium, what kind of a charge does the potassium have? +1. Boom. So now you only have 1 unknown. This is +1, this is -2. So we can 2 +1s +3 +1 plus iodine, don't know what hell that is, whatever, +6 -2s. What does the whole thing have to equal? What's the whole charge of the entire thing? 2. Whatever number cancels all the crap you have remaining. Is that okay? What was the key to solving this question? Deal with the ions separately. Any ionic compound. Every ionic compound. All the ionic compounds. Yeah.
I should end up with a 0.
Yes. What is oxygen always?
Plus, oxygen is minus 3.
Yeah. So yes, you should end up with 0. Question? John? Okay. Is that an ionic compound? No. No. So you can't deal with the ion shuttles. Oxygen is always. Right? Because it's not an ionic compound, you can't deal with it. Because where did you get the minus 3 from? From Boston, just okay, so it's a molecular compound. Is this an ion? Yeah. Right? Is this made of ions? Positive ions. No. I don't know. What is the definition of ion? It's a metal or like ammonium and right? So this is a metal non. Well, okay, it's a metal and something else that isn't charged. This is a compound. So we have to treat
I don't.
this is Al. Let's find HCO. Well, yeah, usually it's in, but maybe it's too long. Let's just do it like this. Okay,
I have stairs.
now it's the carbon that we you don't mind. I'm just trying to figure out that's what I'm trying to go through. I'm trying to figure out what
You can do it.
Oh, you could. If you want to do that, then you could. Nope. It's going to work out okay. Now, this, okay, we're going about doing this the complicated way because I didn't think we could just treat that as a one-line sign. Is that okay? Yeah, so if, okay, so let's just offer fiber and HCO3 naked. So now treat this the same way we're treating the line. And try and figure out what the carbon is.
No.
Hydrogen.
See? Why? Huh? Why? I just read resenting my yesterday. Yeah, so I don't know what to say.
Carbon plus negative one ion.
I don't know.
That's tough, right? Tough. Yeah. 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 Absolutely. What kind of compound is this? Yeah. So it's an ionic compound. So the aluminum is the positive. What's the negative? Everything else. Yeah, HCO3, right? So let's let's look for HCO3. Find HCO3. Hydrogen carbonate. What kind of a charge is that? It's got a negative 1 charge. So we can just treat it as an ion. HCO3 if we wanted to. Yes. Okay, I'm gonna kind of reveal the answers here. Well, actually not kind of. I'm just gonna reveal all the answers. So, what I need from you, there is 7 minutes left in class. What I need from you right now, I need you to tell me if there's anything on here that you don't get. If you're like, how the hell did he get that? Then I need you to tell me right now, because it's really critically important that you understand this today, because we're going to do a little bit more tomorrow, and then we're moving on, and I expect you to have this tool in your tool belt, because it is the fundamental principle of redox. Isaac.
So, for using K2H3IO6
Yeah.
as an example, so we were looking for I, for the
Yeah.
iodine.
Totally.
But
Yeah.
like, if it said to focus on like on potassium instead of
Yeah.
iodine,
Yeah.
then I would have put down iodine's oxidation level as like -1, because that's what its
Okay.
is, right? So I'm just confused about like the deductive reasoning here.
Okay.
I think I zoned out for part of your
Yep.
explanation, so I'm sorry if
Yep.
this is obvious, but
Okay, I need everybody to pay attention, because I'm going to ask this like a lot. I've asked this a lot in the past, and I'm going to keep asking it. Is this an ionic compound?
Yes.
Then it is made out of ions.
yeah.
What are the 2 ions that make up this compound? Potassium ions. So I'm going to write it out. I'm going to write it out as if like they're separate ions, okay?
Okay.
So we've got potassium ions. What kind of a charge does a potassium ion have to have? +1 is the only option.
Yeah.
So there's 2 of them, right?
Yeah.
Okay. Now that means everything else altogether,
Yeah.
all of this crap is one huge massive ion.
Okay.
This is an H3IO6 ion. And what does this ion have to have as a charge? You've never seen this ion before in your entire life.
Oh,
But
yes,
what
I got
kind of a
that.
charge does it have to have?
Okay. Right.
Would you agree this has to have a -2 charge?
Yeah. Okay.
Why?
Because it has to
It has to balance out the positive charges brought by the potassiums, right? So this whole thing has a -2 charge. So deal with it as if it was a complex ion. Now the problem is that Isaac, there's like a whole crap load of covalent bonds going on inside this thing, and you have no idea what the structure is. There's a buttload of ionic or covalent bonds.
Yeah.
Is this an iodide ion all by itself? Is this an iodide ion all by itself? No, it's a hydrogen superiodate, whatever the hell this is. Okay. So you can't treat this as an I minus all by itself, because it's got a bunch of bonds.
Yeah.
So we say, okay, this is +1, this is -2, and we don't know what the hell that is.
Yeah.
So 3 +1s and an iodine and 6 -2s has to equal -2. And then you just figure it out.
Yeah.
Is that okay?
Yeah, I did solve it.
Yeah. Yeah, that's fine.
Thank you. Sorry about that.
Yeah, but to answer your question, if it said what's the oxidation state of potassium, what is it?
Well, one.
+1. Yeah, but that's easy peasy, right?
Okay, yeah.
Because it's an ionic compound.
I think I'm confusing it with the charge of the ions.
Yes.
I'm kind
But well, what you're confusing, and I don't mean to like really stick on it,
That's
is that this is not an iodide ion.
Yeah.
If it was an iodide ion,
Yeah.
as just all by itself as a negative ion, then it would be I minus, right?
Yeah.
Okay, Shahad, you had a question. Don't start
Yes.
packing up. Shh.
CR207. I don't know how you get the +6.
Okay, so CR207, 2 minus. So the whole thing has to equal -2. We don't have a rule about chromium, but we have a rule about oxygen. What is oxygen?
-2.
So 7 -2s. And how many chromiums are here?
2.
2 CRs. Right? So this is 2 CR minus 14 equals -2. They're just solving for a single variable, right?
Okay.
Add 14 on both sides, so 2 CR equals +12. And divide by 2, CR equals +6.
Okay.
Is that okay?
Yes.
Yeah. So it's if you can find an intuitive way of doing it, then go ahead and do that. The way I think about this is I say there's a total of -14 here, right? Do we want to cancel out all -14?
No.
No, we want to cancel out 12 of the -14. So 12 divided by 2 is +6.
Okay.
That's the way I think about it.
Thank you.
But whatever, that's okay. So tomorrow we'll do a little bit of a recap on oxidation numbers, and we will try and figure out how you can tell if a reaction is oxidation like redox, basically.